One of the things that we humans do really well is to find patterns in our natural world. The periodic table of the elements represents the fundamental map that we humans use to understand the building blocks of our physical world. We take these elements and configure them chemically, physically, and geometrically to create devices that can perform almost miraculous functions. Let's begin our journey by considering the humblest of all electrical devices, a piece of ordinary copper wire. In the element copper, the electrons are only loosely bound. This allows them to freely move from one atom to another. This makes the material highly electrically conductive. If we take a rod of this copper material and surround it coaxially with a tube of an insulating material, one where the electrons are not free to move around but are rigidly attached to their atoms, we can create a uniquely useful configuration. We create what is fundamentally a pipe for electricity. Electrons can go in one end, but they can't escape through the insulation. They can only get out at the other end, where the insulation has been removed. With this simple configuration, we can control where electricity goes to great effect. So what I've got here is my favorite physical metaphor for the flow of electricity in a conductor. I've got my bowl of electrons, and I have my conductor, which is metal. And this metal has the property that electrons can freely move from one atom to another in this matrix. So if we look at this, the electrons don't move. They just sit there until we apply an electromotive force. And this electromotive force causes the electrons to move. And the flow of these electrons and the rate which they flow is equal to the magnitude of the current that flows in this conductor. So as I do this, the electron that goes in is not necessarily the one that pops out. It's just shifting through this lattice of atoms, and the nearest one to the end is what we see popping out here. Now to do this, I've got to apply a force, and I'm doing work. The balls have friction as they go through this tube, and that's exactly the analogous thing that happens with a wire, that the electrons go through this imperfect medium and there's friction, and that friction then creates a loss of energy, and that loss of energy is manifested in heating up the wire. Just as if I could shove these balls in here as fast as I possibly could, I probably could heat up this tube slightly just because of the mechanical friction of them sliding along the inside of the tube. So in that way, it's a perfect analogy for what actually happens in a wire when electricity is flowing through it. Now we can see that it takes a force, an electromotive force, to get those electrons moving. So where does this force come from? Well, let's consider the simplest and probably most familiar source of electromotive force, a battery. A battery is a device that converts chemical energy into electrical energy. Inside of a battery, we have an arrangement of chemical elements that produces an electromotive force between one part of the battery and another. This electromotive force can now force electrons to move. But they're still not going to move until we provide a clear electrically conductive pathway from one terminal of the battery to another. This is what we call a circuit. Now, the dictionary defines a circuit as a roughly circular line, route, or movement that starts and finishes at the same place. And that's exactly what's going on here. The electrons that are separated by these electrochemical forces are pushed around the circuit until they return to the battery, where they recombine with the atoms inside, forming new compounds, thus completing the chemical reaction. But if we just connect a wire across a battery like this, all we're doing is shorting it out. All that chemical energy in the battery just goes into heating things up. You're going to end up with a very hot and angry battery, and if the current is high enough, maybe even some melted wires. But if we connect an appropriate electrical load to the battery, like a light bulb or a motor, we can make it do useful work, converting that chemical energy into something beneficial. Now, it's often said that electricity takes the path of least resistance, but it's much more accurate to say electricity takes all available paths. You'll often see in circuits that the current takes many paths, all of which converge to a single return. The current flowing out of the power source is always equal to the current that returns to the power source. Okay, now there's one important thing I gotta really clean up here. Back in the day when they were figuring all this electrical stuff out, the convention got started that electricity flowed from positive to negative. When they discovered the negatively charged electron and realized that these things flowed from negative to positive, it was already too late. The convention had been established and there was no turning back. So forget about electron flow. That's completely not helpful to you in your study of electronics. Unless you're learning about vacuum tubes or solid-state physics, conventional current flow is what you're concerned with, and it flows from positive to negative. End of story. While it might seem easy and convenient to just use pictures to represent electronic components, this approach quickly dissolves into a sketchy and ambiguous mess. Instead, we use schematic symbols to graphically represent components. Take the schematic symbol for a battery as a good example. The original battery is basically a stack of little metal discs separated by pieces of paper that are moistened with an electrolyte. And if you think about it, the schematic symbol is a fairly clear representation of that. You can see it when you compare the real picture to the diagram. And most schematic symbols are derived exactly this way. They're sort of like simplified abstractions of the actual parts they represent. This idea makes it pretty easy to remember what they are once you get the hang of it. Here's an actual power resistor. You can see it's just a ribbon of some high resistance metal that's scrunched up and wound around a piece of ceramic. The symbol is just a simple zigzag line. It's not a loop because that might be confused with a coil or an inductor. So what are these resistor things anyway? Well, besides being the most ubiquitous and mundane electronic components, they're just fundamentally an arrangement of material that electrons have difficulty getting through. They have resistance, and that just means they resist the flow of electrons. If you place a voltage across the terminals of a resistor, a current will flow. That current will be limited by the resistance and proportional to the voltage. Now conversely, if you take a resistor and you make a current flow through it, a voltage will appear across its terminals that's proportional to that current and the resistance. Now take careful note of my choice of words there. When I say a voltage across, I'm referring to a difference in voltage between one end of the resistor and another, and that results in a current through the resistor. This may seem like a trivial detail of language, but it's actually a really critical part of really understanding what's going on. Let's do a simple little experiment to try to illustrate the relationship between current, voltage, and resistance. I have three resistors. I have a 1 million ohm resistor, a 470 ohm resistor, and a 10 ohm resistor. All three of these resistors are rated for a maximum power of 1/4 of a watt. Watch what happens when I connect these resistors to a 12-volt battery. The 1 million ohm resistor sits there and does almost nothing. The resistance is so high that the magnitude of current that's flowing in this circuit is extremely low. Basically nothing much happens except a very tiny current flows. This small current flow represents a very minuscule amount of energy that's flowing out of the battery. It's not enough to heat up the resistor or do anything significant. Now, if we repeat the same experiment with a 470 ohm resistor, now you can see that this resistor is actually getting pretty hot. It gets up to about 60 degrees Celsius, which is because this lower resistance allows a much larger current to flow, which causes significant heating in the resistor. And now we can see that a moderate amount of energy is flowing from the battery into the resistor. Repeating this now with the 10 ohm resistor, in 5 seconds it's toast. A huge current has flowed through the resistor, which caused the resistor to completely overheat beyond its normal limits, vaporizing the resistive material inside the resistor. Basically, it opened its own circuit and shut itself off because there was nothing left to conduct electricity. Now note that in all 3 cases, the amount of energy that flowed out of the battery was determined solely by the external resistance of the circuit. The lower the resistance, the larger the current, and the more power was drawn from the power source. It's important to understand that the battery isn't pushing amps. It's merely supplying an electromotive force that's being resisted by the resistor. The only way you could increase the current would be by reducing the resistance or increasing the voltage. Now coming back to the big picture here, electronics is really all about managing the flow of energy in a clever and useful way. And we've seen by selecting different resistors, we can control how much energy is liberated from the battery and turned into heat. Now that heat isn't really very useful in this context, but if this load was an LED, for example, that energy would be transformed into light, which is very useful to us. Now, energy or power in electronic circuits is measured in units called watts. To determine the number of watts that are being dissipated by a resistor, you take the voltage that appears across it and multiply that by the current that's flowing through it. The same idea also holds true for power sources. If a 12-volt power source is delivering 1 ampere of current, it's delivering 12 watts to its load. Now you've heard me talk about amps, ohms, watts, and volts. All of these units are part of an elegant system that makes beautiful sense. They're completely related. If you take a 1 ohm resistor and you apply 1 volt to its terminals, a current of 1 amp will flow, resulting in a power dissipation of exactly 1 watt. It's all related and it all makes sense.